Hi, I'm John Whitney. I spent more than 30 years as a chemical engineer doing design, process development, and product development, as well as production, engineering, and quality management for several industries. I'm here to talk to you today about what design looks like from the perspective of a chemical engineer. While all of the engineering disciplines share a lot of the same parts of the design process, there are things about each that make them a bit unique. Chemical engineering spends a lot of time with gases, liquids, and powders, chemical reactions, heating and cooling, mixing and separating. Modeling for this can be quite good, but often is not as good as trying it on the actual full-size equipment. One of the things that's more special to chemical engineering is the need to be doing your testing then on the actual large production equipment. This means that every test is potentially creating very large amounts of worthless scrap. You can't just jump in and try a few things quickly. Another more special thing to chemical engineering is that you're frequently designing at the interface of process equipment and the materials used by that equipment. You're designing the two together to bring out key features in the other to get a unique result. Let me give you two examples from my career. Example 1. We're using scrap plastic film. The product we made was 2 of the 7 layers of a potato chip bag. It was a special type of plastic film, biaxially oriented polypropylene, with a heat sealable adhesive layer on it so the flat film could be sealed in the individual bags. The film was made using a bubble process, where at the top of a tall building there were large extruders melting and filtering plastic and pumping it through a round die to make a continuous plastic tube. The tube is frozen, reheated with infrared heat, just enough to soften the plastic so it could be stretched. Yet it is cool enough so the molecules still entangled with each other, so the bubble stretched. The molecules that used to be randomly oriented are all lined up in one plane, the plane of the plastic film. This meant that the two axes of the film had a 30,000 psi tensile strength, as strong as a low-carbon steel, but the plastic film was very weak in the third axis, the thickness of the film, because very few of the molecules were oriented in that direction. That's why, if you're pulling on a potato chip bag on the ends to open it, you'll probably fail. You're pulling the same plane as the film strength. But once the film is cut or torn, it tears very easily because you're pulling across the film's weak axis, the thickness of the film, and it opens very easily. The problem was that we wanted to recycle manufacturing scrap. All the manufacturing scrap was put in a landfill, and that was expensive. When the scrap film with adhesive layer was put back through an extruder, the adhesive molecules would break down into shorter molecules due to the heat and mixing in the extruder. Even though the plastic was all mixed up in the extrusion process, when the plastic came out, the last little bit of the die, it went from high pressure to room pressure very quickly. This differential pressure caused the shortest molecules to slip past the longer ones and concentrate near the surface of the plastic. These short molecules of adhesive would stick to the exit edge of the metal die, forming little brown stalactites. As time went on, the stalactites would grow and break off. When the brown speck made it to the infrared heating part, it would be heated more because it was dark and caused the bubble to pop. Well, actually, when a bubble is 5 foot diameter and about 50 foot long, it doesn't so much pop as it goes boom, and dust is shaken off the rafters, and everybody around knows it. It then takes 1 or 2 hours to get back to making good product, and in that 1 or 2 hours, you're making scrap and costing the company several $1,000s an hour. The solution had 2 parts. The first part was to create a die that let the polymer expand more slowly so that the short adhesive molecules did not slip past the longer ones and push their way to the surface of the plastic tube. If that transition was too slow, then we would not control the film thickness and keep it even. So there was a strong trade-off here. The second part was like using a Teflon coated frying pan to keep eggs from sticking to the pan. The dye lips were coated with a Teflon to reduce the proportion of short adhesive molecules that stuck to the dye instead of continuing with the plastic tube. This also had several trade-offs. The best possible coaters could not make a Teflon as smooth as a carefully machined and polished steel, and the Teflon was very soft and very easily damaged compared to the normal steel dye lips. I was given the responsibility of designing the testing on full-scale production equipment, including determining which types of Teflon to use, determining the method of applying it, finding and qualifying a vendor to apply it, developing specifications for the coating, designing which dye lip contours should be tested, determining how many dye lip sets would be machined. Oh, by the way, once I had these $200,000 dye sets modified, they would be useless for production. I kept getting reminded about that several times. Then I also needed to develop and run the production scale trials, getting buy-in and approvals from production management and maintenance, determining what process test conditions we would try to run, and define what criteria would be used to cancel any part or all of the trial. Train production operators, maintenance, and engineers that would be involved with the trials. Trials required 4 to 6 hours to change over equipment, and then 16 to 48 hours of trying to make it work, followed by another 6 to 8 hours of trying to get back to making normal in-specification product. The 16 hours was if it was a disaster. Nothing in the trial worked. And the 48 hours was the plan if everything worked pretty well. This is on a process that runs 24 hours a day and does not intentionally shut down for many months at a time. Running these tests involved getting engineers and added production operators to cover the days of test time that cost about $3,000 or $4,000 an hour in today's dollars. After several positive trials and adjustments, I noticed that when everything was working well, meaning that the stalactites were not falling off and popping the bubble, the stalactites were turning from a honey brown viscous liquid to a hard black material that was putting scratches into the plastic. The smaller lab scale testing had never run long enough to have this happen. Any polyethylene or polypropylene that is sitting at that temperature and is exposed to air would go through the same change of oxidizing. I needed to keep oxygen in the air from contacting the stalactites on the outside surface of the plastic tube we were extruding, and also on the inside of that same plastic tube. I further modified some dye lips to gently put a curtain of nitrogen gas where the stalactites would form so that they stayed softer much longer, making them scratch less and stay flexible longer. After about 2 years of testing and modifications, we were able to use the scrap plastic and recycle it back into normal production with help from a lot of people, save millions of dollars a year, and put less in the local landfill.